Math SL. Sorry, Math HL. Today we are going to look at lines, planes, and angles. Specifically, how do lines and planes interact, and how do we find angles between them? In the past, we have looked at lines compared to each other. How can we find the intersection of lines? How can we determine if lines are parallel or coincident or skew? We also looked at planes and looked at how they can compare. How do we find the intersection of planes? How do we find the intersection of three planes? How can that happen? Well, today we're going to combine the two, lines and planes. So when we think of a plane and a line, we can have three situations. You might have a line that is in the plane. The line is in the plane. So every single point on that line is also on the plane. We also can have a line be parallel to a plane. Situation like that. So the line would be parallel to the plane, it will never intersect the plane. And then we have a third case, of course, where the line will intersect the plane, and it will intersect the plane in one spot. So it either intersects in infinitely many spots, one spot, or zero spots. So we're going to look at each of those three situations. So we've got our first example here. We've got a plane, 2x plus y minus z equals 3. And then we've got three lines given to us, line 1, line 2, and line 3. We are going to identify which of those three lines is in the plane, which of those three lines is parallel to the plane, and which of those three lines is intersecting the plane. And if it is intersecting the plane, we want to know where. Where is that intersection point? So the first thing we'll want to do to figure out what the interaction or what the relationship is between a plane and a line is we want that line to be in parametric form, or we can put it into a vector form. So remember, we pick a parameter. I'll pick S for this one. And so we want to get X alone, Y alone, and Z alone. And so I'm just going to jump right to vector form here. I think we've done this enough times now. We can sort of figure out what's going on. The number on the bottom of the fraction is ultimately what you're going to multiply times S to get each of those alone. For example, in the Z one, to get Z alone, we'd multiply by 3 and subtract 2. So the component for the direction vector for Z would have to be 3, and then the point would have to be negative 2. So we can kind of do these more quickly now that we have experience. So I'd have to multiply the 2 over, and then subtract the 1. Here I'd multiply the negative 1 over, and then I'd add the 3. So here is my vector equation of line 1. So what we want to do is we want to think of it in parametric form. We have x equals negative 1 plus 2s, y equals 3 minus s, and z equals negative 2 plus 3s. Well, if we think of them on parametric form, we can easily sort of think that maybe that's going to substitute into here. And if that's what you were predicting, we're right. You're right. We're going to substitute the x, y, and z parameters into our plane. So here's the equation of our plane. We're going to substitute negative 1 plus 2s in for x. We're going to substitute 3 minus s in for y, and negative 2 plus 3s in for z. And you'll notice what we get here is an equation with only one variable in it. So now we're going to simplify down what we've got. Negative 2 plus 4s plus 3 minus s plus 2 minus 3s equals 3. If I add like terms over here, I get 3 and I get 0s. So if I solve this, I end up with 0s equals 0. Well, no matter what s is, this is just going to be 0 equals 0. So I have an identity. I have something that's true no matter what s is. No matter what s is, I get something true. Which one of those three scenarios might you guess that this is? If you guess that this is where the plane is on the line, that is the correct guess there, because every single value of s, no matter what it is, will result in a true statement. So this would be the situation where line 1 is in the plane. You could say on, that would be okay as well. Okay, let's examine line 2. And we're going to see what relationship it has with our plane 2x plus y minus z equals 3. I'm going to start the same way. We're going to do the same steps for each one. The difference is what answer we get. What does that answer mean? So now I'm going to look at line 2 here. So I think I'm going to make this parameter t. So I'm going to times the 1 over and add 2. So the number I'm timesing over is the direction vector, and the number I'm adding or subtracting is my position vector. Here I'm going to multiply over 2 and add 0. I do need to fill the spot. Here I'm going to multiply over 5 and subtract a 1. Okay, so there's line 2. Now I'm going to repeat the same steps I did before. I'm going to substitute in the x component, the y component, and the z component and see what happens. So I'm going to take 2x plus y minus z equals 3 again. So in for x, I'm going to substitute 2 plus t. In for y, 0 plus 2t. And in for z, negative 1 plus 5t. And let's simplify this down. I'll get 4 plus 2t plus 2t plus 1 minus 5t equals 3. So I get negative t plus 5 equals 3. So negative t equals negative 2. So t equals 2. So what this means is that the only place where these are in the same spot at the same spot would be at t equals 2. So the only overlap between the plane and the line is when t equals 2. T equals 2 is associated with a specific point, and we can find that specific point by substituting t equals 2 in. And now I can multiply out and see what my solution, where is the point of intersection for this problem. So 2 plus 2, I get 4. 0 plus 4, I get 4. Negative 1 plus 10, I get 9. So at the point 4, 4, 9, I have my point of intersection. So there's one more situation to explore, and that would be line 3. And you're smart people, so you're probably figuring out that if we've done that line 1 was in the plane, line 2 intersected at one point, then line 3 is probably just going to be parallel with the plane. So we're going to see what that looks like. Same situation, I can take line 3 and I can set it equal to some parameter. I guess I'll use lambda. I used s and t already, I'll use lambda this time. So I'll multiply over negative 1 and then add 0. I'll multiply 4 and then subtract 5. I'll multiply 2 and subtract 3. So now I'm going to repeat that process of substituting in each of my x, y, and z components into the equation for the plane that we have. There's the equation of the plane. So we'll get 0 minus lambda plus negative 5 plus 4 lambda minus negative 3 plus 2 lambda equals 3. And let's see what happens here. We get negative 2 lambda minus 5 plus 4 lambda plus 3 minus 2 lambda equals 3. So let's see, I get negative 2 lambda, 4 lambda, and negative 2 lambda. Those all cancel. So if I simplify my constants here, I get negative 2 equals 3. That, of course, is not true. So since it's not true, that means there are no places where the line and the plane intersect. So this would be the case where they are parallel. So line 3 is parallel. Did we give this plane a name? Let's give it a name. pi 1, pi sub 1. I guess I could just call it pi because there's only one of them, but I'll call it pi sub 1. So L3 is parallel to pi sub 1. So that's how you figure out if a line is either coincident with the plane, meaning in the plane. I guess coincident isn't exactly the right word. Line 1 is in the plane. Line 2 intersected at one point, and line 3 was parallel. Okay, so we've looked at how lines and planes can interact in the sense of where is their intersection. Now let's look at the angles between things. That's the second part of our lesson here. We already know how to find the angles between two lines. We've done that before. We do the dot product of their direction vectors. The dot product of their direction vectors can tell us the angle between the lines. What about two planes or a plane and a line? Well, first let's look at the two planes example. So if we're looking here, the angle that we want is we want the angle, typically we find the acute angle between these two planes. So we want to figure out what theta is right there. Well, it's kind of weird, but we're actually not going to find the angle between the planes directly. What we're going to do is we're going to find the angle between their normals. And that's going to be the same as the angle between the planes. So the angle between the normals is the same as the angle between the planes. And the normal is a vector that's perpendicular to a plane. So we're making it simpler by taking something that's a plane, but instead we're thinking of the normal, which is just a vector. Remember what a normal is? A normal is perpendicular to something. So let's see if we can kind of picture this. Let's say I want to draw the normal to plane Q here. I could draw, let's say this is the point on Q where the normal begins, and it goes this direction. So that's the normal to plane Q. Now let's think of the normal to plane P. Let's just start it right here. And we're drawing a three-dimensional situation on flat paper. So things might look a little bit weird, but we're going to draw the normal or the perpendicular vector to this plane P. So I'm going to draw it so that it looks like it's perpendicular to that plane P. Now what we're actually finding here is we're actually finding this angle here. Or you can think of it as this angle here, same difference, right? That's the angle we're actually finding. But do you see that even in my rustic drawing, that does appear to be the same as the theta I drew originally? So if you have things that, if you draw normals, the normals are going to be at the same angle as the planes are. So remember the way to get a normal vector from a plane. Let's call this pi 1 and pi 2. The normal to pi 1 is going to be 3, 2, 1. It's just the coefficients of x, y, and z. The normal vector to plane 2 are just going to be 1, 2, 4. Oh, there should be a z here. That's a typo. There should be a z there. That's just missing on accident, okay? What if there wasn't a z there? If there wasn't a z there, then actually be 0 z, so you'd put a 0 here. But I do know that that is a typo. But let's say that was just a 4, and there was no z. If there's no z, you just put 0 here, okay? So we want the angle between the normals, really. So we're going to do the dot product. So you're going to do the dot product of their normals. So 3 times 1 plus 2 times 2 plus 1 times 4 equals the square root of 9 plus 4 plus 1 times the square root of 1 plus 4 plus 16 cosine theta. Okay, so let's simplify as much as we can here. We've got 3 and 4, so that makes 7. So we have 11 over the square root of 14 times the square root of 21. And we'll just do the inverse cosine of that. Now, it does not say if they want radian or degree form. I'm going to go with degrees here. If it says radians, of course, you'll want to make sure that you are in radian mode. But usually when we're finding the angles between things, we use degrees. So inverse cosine of 11 divided by rad 14 times 21, we can combine that all together. So we get about 50.1 degrees if we're rounding to 3 sig figs. So 50.1 degrees is the acute angle between these two planes. If the answer came out obtuse, well, that would just be this angle here that we'd be getting. And you can just simply subtract from 180 to get the acute angle. If they say, it's typical for us to give the acute answer in these cases, by the way. Okay, so we looked at how to find the angle between two planes. Lastly, what if we need the angle between a line and a plane? So here's a diagram here that kind of shows what we want. We want the angle between this line here. I just picked an image off Google search. So they've got a bunch of subscripts we might not need. But here's my line, and then here's my plane. So this is the angle I want here. If I think about this as being a line on that plane that's going in the same direction as L, that's the angle I'm going to want, the angle between the line and the plane. Well, you can kind of already see that they drew the normal on there. I'm not sure why they didn't just draw the normal right here. That would have been where I would draw the normal. But what we're going to do is we're going to find the angle between the line and the normal. Because what appears to be true about the angle between the normal and the line and the angle between the line and the plane? Well, these two together would have to be complementary. They would have to add up to 90. So that's our strategy here. So the strategy of finding angles when a plane is involved is to use the normal, okay? So we've got this line here. We need the line to be in vector form. I'll use the parameter t. So I'll times the 2 over and subtract 3, times the 4 over and add 5, times the 2 over and then subtract 3 and divide by 3. So that'll be -1. And then the normal, let's call this guy pi, p sub 1. So the normal to that is going to be 5, -1/4. We just pull the coefficients from the Cartesian equation of that plane. So now we're going to do the dot product between the direction vector and the normal. So 5 times 2 plus -1 times 4 plus 4 times 2. This is an important reminder that dot product is commutative. It does not matter what order you do them in. Okay, now for the radical parts, we've got 4, 16, and 4. By squaring those, by squaring these, we get 25, 1, and 16. And then cosine theta. And from here, it's roughly the same steps as before. We're going to get 10 minus 4, which is 6, plus 8, which is 2, divided by rad 24, rad 50, no, it's Friday afternoon, 26 and 16, 42. And then that equals cosine theta. Okay, so inverse cosine 2 divided by the square root of 24 times 42. Okay, so I get 86.4. Let's hold off on rounding though, because as you recall, this is actually not my answer. This is the answer to the angle between the normal and the line. We need to find theta, so I'll call this maybe like theta sub 1 to distinguish it from regular theta. So to find theta, we're going to do 90 minus that. Oops, my degree symbol's a little off, whatever. About 3.61. Remember, we want 3 sig figs there, so that's what we needed to do. So notice that as long as I didn't make any arithmetic errors here, which is always possible, It is a very small angle between the line and the plane. Okay, so I think that's it for this video of how to find how lines and planes intersect, as well as how to find angles between planes and angles between a line and a plane. That wraps it up for this time.